Hello, this is the final video in the mini-series on combinatorial games as part of these problem-solving videos. We're going to finish off looking at the technique of pairing. As a refresher, we want to look at all possible moves in a game and try and pair them up so that one player can always mirror their opponent's moves by making the paired move, and in so doing either draw or even win the game. Last video, I gave you 3 games to think about. One-dimensional noughts and crosses. The first game is normal noughts and crosses, but played in an infinite row of squares. This version of noughts and crosses is so simple that finding a strategy to guarantee a draw intuitively is easy. Player 2 should always just play in a square adjacent to the square in which player 1 has just played. Checking a couple of cases, you can see that the best player 1 can do is 2 in a row. It is worthwhile, however, trying to use pairing more explicitly because it will help with our next problem, which is a lot harder. The idea is to pair up adjacent squares. There are 2 ways to do this, and either works. Now, wherever player 1 moves, player 2 simply moves in the paired square. This strategy is subtly but importantly different from the previous one. Once the pairing has been chosen, player 2 doesn't have to make any choices about where they play, whereas before they sometimes have to choose whether to play on the left or the right of player 1. Also, this strategy is particularly amenable to an elegant proof that player 2 can't lose. Choose any row of 3 consecutive squares in which player 1 wants to make 3 noughts in a row. Well, these 3 squares include a pair of squares, so will end up containing a nought and a cross, and so cannot possibly be 3 noughts in a row. 5 in a row noughts and crosses. That solution may seem a bit over-engineered, but the benefit comes when trying to solve the 5 in a row 2-dimensional version. If you thought about this game and tried finding a strategy without using pairing, I'm willing to bet you struggled. Trying an intuitive approach, as we did with the 1D game, you'll find that there are just too many degrees of freedom in how player 1 can move to write down a clear strategy of how player 2 should move. However, we can try and generalize the pairing strategy with ease. In the first game, we paired up squares so that any run of 3 squares contained a pair. Now we want to pair up squares so that any run of 5 vertically or horizontally contains a pair. Remember that diagonals are not allowed. Playing around on some paper for a minute or so, it's easy to find a suitable pairing. Here's one possibility. And here's another. You might ask why I excluded diagonals from this game, while diagonals are allowed in regular noughts and crosses. The answer is that if you do include diagonals, no one knows whether there's a winning strategy or a strategy to force a draw. You can pretty easily convince yourself that a simple pairing strategy won't work to force a draw, but this doesn't mean that there isn't some other clever strategy that will work. If you're interested to find out more about variants of noughts and crosses, I read about this open problem in the book Combinatorial Games, Tic-Tac-Toe Theory by Joseph Beck, which consists of 732 pages just on variants of noughts and crosses. Jumping coin game. The third game takes place on a 7x7 board. Starting with a coin in the center of the board, the players take it in turns to move the coin to a new square, with the rule that they must move the coin further than their opponent did on the previous move. It is possible to move the coin to any square on the board, and notice that these moves pair up in a similar way to the moves in the game of Misère noughts and crosses, with the exception of the central square, which we'll come back to momentarily. The obvious strategy to try would be for player 2 to mirror player 1's moves, and always move the coin to the paired square of wherever player 1 leaves it. For a minute, let's assume that this is always possible within the rules of the game, and check that it is indeed a winning strategy for player 2. Since one of the players must be unable to move eventually, we conclude that this is player 1, since if player 1 has just moved, player 2 can also move to the paired square. Now we just have the not insignificant task of proving that the strategy is valid. For this, we need to check two things. Firstly, that player 1 can never move the coin back to the centre, because then there will be no paired square for player 2 to move it to. And secondly, that whatever move player 1 makes, player 2 will always move the coin further by moving it to the paired square. The first point is easy. From the pairing strategy, the distance player 2 moves the coin on their move is always twice the distance from where it ends up to the central square. Player 1 then must move the coin even further still, so certainly cannot move it back to the centre. Proving the second part is a bit trickier. There are a couple of ways of going about it, but I think the slickest way is to use the triangle inequality. Remember that this says that in any triangle, the sum of the lengths of any two of its sides is greater than the length of its third side. Now suppose that it's player 2's turn. If it's player 2's first turn, they will clearly move the coin twice the distance player 1 just moved it. Otherwise, say that player 1 has just moved the coin a distance b. From player 2's pairing strategy, we know both where the coin must have been before player 1's turn and where player 2 will move it on this turn. Let's say that player 2 moved the coin a distance 2a on their previous turn and moves it a distance 2c on this turn. Since player 1 must have made a legal move, we know that b is greater than 2a. It will actually be useful for us to swap the inequality over and write minus 2a is bigger than minus b, as you'll see in a second. Now look at this triangle. From the triangle inequality, we know that a plus c is bigger than b. If we subtract a and multiply by 2, we get 2c is greater than 2b minus 2a. But minus 2a is bigger than minus b, so 2c is greater than 2b minus b, which is just b. In other words, player 2's move by a distance 2c is further than player 1's previous move of b, so it is a legal move. To summarise, player 2's strategy is always to move the coin to mirror player 1's move. This is always possible because player 1 cannot move the coin back to the centre, and player 2's move will always be within the rules. This means that whatever player 1 does, player 2 can always follow it with a legal move. Therefore, since one of the players will not be able to move eventually, this must be player 1, so they lose and player 2 has the winning strategy. Notice also that there's nothing special about the board being 7 by 7. The same thing will work on any square board with any odd size. What if the board was made out of some different tessellating shape other than squares? Equilateral triangles, or hexagons, or even a shape which isn't regular? Leave your ideas in the comments below. I'm going to leave you with one more problem to think about, although I won't go over the answer in the next video. Still, have a think about it and put your ideas in the comments. If you get stuck, you can always check there to get an idea of how to solve it. Who let the horses out? Start with a standard 8x8 board. The first player puts a chess knight on the board on each of their turns, and the second player makes a legal move with one of the knights on each of their turns. No knight can be placed or moved to a square which is or has previously been occupied by a knight. Whichever player cannot move loses. Which player has a winning strategy? Thank you very much for watching. I hope you've enjoyed these videos on problem solving and game theory. In the next video, we shall start a new mini-series on problem solving. This series will be focusing on using invariance, an extremely important problem solving technique which turns up in every area of maths. As usual, subscribe to be notified about new videos.